Assalamualaikum and good afternoon. Today I would like to share with you about pumping system and the theoretical and its tutorial. So in this slide, we focus to answer a few questions. There are two basic idea of pumping system here. So for example, we have a pump system problems number one. Two identical pumps are connected to a pipe system as shown in figure 4. The pumps are used to deliver water into the high-level reservoir. The head discharge characteristic of the pumps is given by equation 1. So this is the equation 1, where Q is the pump discharge in liter per second and H is the head developed by the pump. The pipe AB is 150 meter long with a diameter of 300 millimeter. The pipe BC is 250 meter long with a diameter 400 millimeters. The friction factor for both pipes is 0.03. The regulating valve V is used to regulate flow in pipe BC. The static lift against which the pump are working are 40 meters and 70 meters. For a given of valve, the pump operates against a static lift of 70 meters and develop a discharge of 100 liters per second. Determine the discharge of the second pump and the loss of coefficient of the valve. Neglect all minor losses and pipe loss from B to tank 2. So this is the question, and the illustration of this question is show like this one. So here we have a one tank here. So and then we are using pump to pump water into point B, and then we have a water here, and then we have another pump here. So usually in this setting, we could assume that these two water tank, these two water source will be pumped by using these two pump into this third tank. So and then we need to calculate a few things. Okay, so from the question here, we need determine the discharge of the second pump and the loss of coefficient of the valve. So we need to calculate the discharge of the second pump here. But what you need to understand is, so the discharge here is actually the sum or the total discharge from pump number 1 and pump number 2. So we could start to calculate this one by having a Bernoulli equation from tank 1 to tank 3. So this is tank number 1 and this is tank number 3. So before you use Bernoulli equation, please understand the real meaning of the basic idea of Bernoulli equation. So Bernoulli equation is actually reflect the energy of the streamline. So means that what you need to do is you need to imagine from where the molecule of fluid travel from where to where. So for example, if we have a tank A here and tank C, we have a tank B here. So we imagine that a water molecule from tank 1 here will travel into this pump, and then they will go to tank number 3. So means that you only could compare the energy by using the Bernoulli equation only from point 1 and point 3 only. So you can, because in this situation, the molecule of water from tank number 1 here did not enter point number 2. So means that we cannot compare Bernoulli energy from tank number 1 with tank number 2, because the streamline is not exist from tank number 1 to tank number 2. So this is the basic idea to determine when you want to use or when you want to compare the energy by using the Bernoulli equation. So we compare tank number 1 and tank number 3. So I hope you still remember the Bernoulli equation. We have rho P over rho G plus V square over 2G and plus Z. So and then for inlet here, so we will have an atmospheric pressure here, and then the velocity is start from 0, and also we assume that this is maybe the datum. So mean this is the datum. So the height is 70. So and then the height here is 40. So means the difference here is 30. So means that we assume that this line will be the datum of this calculation. So means that the pressure is atmospheric pressure, the velocity is start from 0, and the elevation or the datum is equal to 0. So we have a 30 here, and then you know when we have a pump, so the head of pump will be appear in the inlet. So this is the inlet of this equation. So we have head of pump for pump number 1. So and then at the outlet here, so we have the pressure and velocity here. So we assume that when the velocity from here up to here, so we assume that okay, the pressure is get back into atmospheric pressure, and then the velocity will end as a static molecule. So and then the level here is 70 meters. So we could substitute into the equation here with 0 pressure, 0 velocity, and the height here is the height is the elevation is exists. And then you could check the Bernoulli equation here by having a simple assumption. For example, according to this equation, we found that energy from the pump will be added into the fluid, into the streamline, into the flow, and then because the flow having more energy, so the fluid can go to the upper level. So means that that's why in this movement we found that water could travel from lower place to 70 meter above the datum. Why fluid could elevate into this high? Because it get extra energy from the existence of pump here. So however, we learned about the major loss and minor loss in fluid mechanics 1 and 2. So we need to add the value of losses here in our Bernoulli equation. So this is the major losses for pipe A, which is from here to here. So and then this is the major loss for pipe B, which is from here to here. So and then this is the minor loss for valve. So we have a valve here, and we cannot neglect the existence of the valve. Maybe we could neglect the minor loss of the inlet, of the bending pipe, and so on and so forth. But in this system, it is obviously we cannot neglect the existence of the valve. So and then in this calculation, I hope you could really understand when we want to calculate the major losses. Okay, we must make sure that the coefficient of friction, or the friction coefficient, and the velocity is the same. So according to this diagram, we found that we only have one pump here. So we have a velocity of VA. And then start from point B here, the flow will become faster because the flow here is depend on pump number 2 and pump number 1. So means that flow from point B here until this water tank will have an extra energy comes from pump number 2. Okay, so and then from the question, we know that the flow rate is 0.1 meter cube per second. So we could calculate the velocity of VA. So by dividing with the cross-sectional area, so we get it is equal to 1.41 meter per second. So we substitute into this equation. So we will have this one. So and then Okay. So and then we have equation given in the question. So this equation is to calculate the head of palm for this situation. So please do not remember this equation because this equation only valid for this problem. So and then if we substitute the value of Q here, so and then we could get that head of palm is given as 76 meters. So and then we try to do another Bernoulli equation from point number 2 and point number 3. So and then we could get this one. So and then we could have the head of palm for 2 is equal to this equation. And then we could rearrange to become equation number 4. So and then we go back to into equation from equation number 1 and number 2 here. Okay, so and then we could substitute the value of 76 into this one, and then we could rearrange the equation to have only the terms of VB here. So and then it is equal with this one. So we have VB squared there. So and then we could from equation number 4, we could solve the problem. So means that we could deduct the value of 0.96 VB square plus 0.05 K VB square, and then we could get that head of palm for point number 2 is 44.48 meter. So and then we could calculate this one by using this equation from the question. So we substitute the value of head of palm for point number 2. So and then we could calculate the value of Q. So and then the value of Q, because it is a quadratic equation, so we will have two value. So we take the positive value. If you get two value and both of them are positive, you need to take the common value or the logic value. So means that if one is 258 and another one is might be 2 or 3 liter per second, so it is good for you to take the logic one, because the flow rate of 3 liter per second might be too small for that setting. So and then from this calculation, we get the value of Q is equal to 258.5 liter per second. So this Q is reflect the flow rate at this pipeline. So and then we could determine the velocity at pipe B, means the velocity after pump number 2. So we use this continuity equation, and then we could determine the velocity is 2.06 meter per second, which is higher compared to the velocity of fluid for pipe B, for pipe A. So and then from this equation, means we have two equation. Okay, I take equation number 4 here. So we substitute the value of head of palm, and then we substitute the value of velocity. So and then we could calculate the value of K, which is the minor loss coefficient for the valve is equal to 1.93. Okay, so for system number 1, it is actually about to connecting 2 or more tanks to deliver fluid with different elevation. So in pump system 1, for example, we have this situation. So let's say we have one tank here, and then it's connected with a pipe and a pump here. So and then it's connected to another tank like this one. So let's say we have the friction coefficient for the pipe is 0.05, and then the length of the pipe is 1 kilometer. So the diameter of the pipe is 0.15 meter, and the pump power is 80 kilowatt. So, and then the question is calculate the maximum flow rate in the pump. Okay, so we know the power is equal to P equal rho GQH, but to calculate the power, we need to know what is the value of H here. So, and then from Bernoulli equation, for sure, we assume that we calculating Bernoulli equation, or we evaluating the energy changes from point number 1 here to point number 2 to other tank. So we substitute the value here. So I think you know why all these parameter is equal to 0. So, and then we have a head of pump at the inlet, and then we cannot neglect the major and minor loss. So in this situation, because we don't have any information for minor loss, so we just use the major loss. So we don't have any information about the minor loss. So the equation will become like this one. So, and then from continuity equation, we have Q is equal AV. So, and then we could calculate the value of velocity inside that pipe by dividing Q with A, and then we change the value of A here with the pi d square over 4. So we have velocity is equal 4Q over pi d square. So, and then we substitute into this equation. So, and then we could have this one, and then we could simplify this as head of pump is 54,390 Q square. So here is actually the hint for you, because in chapter 2, we learn how to calculate the friction and so on by using the idea of losses. HF is equal to Kn Q square. So this is the significance of this idea. Because as I said, I also explained this in chapter 2, when if we are dealing with a pipe system with a larger diameter, so sometimes it reach a fully turbulent condition where the increment of velocity, the increment of Reynolds number is actually not change the friction, not change the value of F. So means that the value of F is again is fixed or constant. No need for us to check the Moody chart to know the Reynolds number, to check the roughness, and then to check the friction coefficient. Because the line, if you still remember, the Moody chart is something like this. So we have a line here. So it's in this region. So means that the line here is almost steady. So mean at any Reynolds number on x-axis will give us almost same value of friction. That's why we could change the calculation of friction as KQ square. So we learned this in chapter 2 about the Hardy-Cross method. So, and then we could calculate the power by using this equation. So we have rho GQHP. So we substitute the head of pump as 54,390 Q square. So we have these terms. We have this value. So if from the question, the power of pump is 80 kilowatt. So we substitute into this one, and then we could calculate that the Q is equal to 18 from 82 meter cube per second. So, and then if we have a situation where the water level is different, so for example, like this one, so we still could solve the problem, but you just start your calculation with Bernoulli equation with the difference of elevation like this one. So means here, so at the outlet here, so the value of Z is equal to 10. So you just add 10 here. So the idea is simple. To make sure that water can be transferred from point number 1 to point number 2 here, you need an extra energy. That's why you must make sure that the head of pump here is bigger compared to the previous system. Compared to the system where the elevation of water is 0. Okay, these two calculation is actually to predict the pipe system connecting two tanks to make sure that it could works in normal condition. So means that if you have the theoretical value and then you could calculate the flow rate and the velocity at the pipe, then if you are checking the real side, you could make your judgment. If the flow rate is not same as your calculation, mean your fully calculation with losses and so on, means that there's something wrong in the real situation. So this is the idea of this calculation.